This video 14 is titled Reducible and Irreducible Representations. Symmetry operations can be denoted by matrices. Consider the transformation of a general point of coordinates x, y, z in Cartesian space under the application of the usual symmetry operations that we do for a molecule, namely identity, sigma reflection, inversion, then proper rotation and improper rotation. Firstly, identity. We know that identity changes the starting coordinates to itself because it is the act of doing nothing. That is x, y, z on identity operation returns to x, y, z. Now we have to denote this change by a matrix equation. The initial set of coordinates and the final set of coordinates is written as a column matrix. Now generate a suitable 3 by 3 square matrix here which multiplies into x, y, z, giving x, y, z itself. Evidently it will be, the first row will be 1, 0, 0 because 1 into x plus 0 into y plus 0 into z will be x. Second row will be 0, 1, 0. 0 into x is 0. 1 into y, it is y plus 0 into z. And the last will be 0, 0, 1. 0 into x plus 0 into y plus 1 into z, and you are getting z. So the matrix created is a unit matrix of order 3. This is why unit matrices are also called identity matrices. Now reflection. Considering the reflecting plane as the principal Cartesian planes, we can denote the reflection operations by the notation sigma xy, sigma yz and sigma xz. We know the effect of doing the reflection on the coordinates of a point is to retain the coordinates already present in the plane but change the one that is not mentioned into its opposite sign. So sigma xz, xy will give, x and y will not change, z changes to minus z. Sigma yz, y and z will not change, x changes to minus x. And sigma xz, x and z will not change and y changes to minus y. These changes are suitably denoted by matrices. Sigma xy, the matrix will be x, y, z, which changes to x, y minus z. So the matrix will be 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Corresponding to sigma yz, matrix will be y and z will not change, minus 1, 0, 0, 0, 1, 0, 0, 0, 1, x, y, z will change to y and z are not changing, minus x, y, z. The third metric equation representing x, z reflection will be x will not change nor the z, y will change to minus of it. So it is x, y, z. On multiplying with this matrix will give x minus y Z. Now the inversion operation. We know that inversion of the set of coordinates x, y, z changes all these to their negative values. So the matrix equation to denote this change will be a negative unit matrix multiplying into x, y, z, so that the answer will be minus x, minus y, minus z, such a column matrix. Proper rotation, next. We assume that the axis of rotation coincides with the z coordinate. So rotation by any angle about the z coordinate will not change the z coordinate of the point. Changes will occur for the x and y coordinates. So the matrix we are seeking will be partly of this type 0, 0, 1, 0, 0. There are 4 missing elements. Finding these 4 missing elements is considered as a 2-dimensional problem of change occurring to a point x1, y1 in the xy plane to x2, y2. The problem can be visualized by this 2-dimensional diagram. This is the x coordinate, this is the y coordinate. Suppose initially we have the point x1, y1. It is denoted by a vector like this. It is rotated in anti-clockwise direction by an angle theta, and it changes to the coordinates x2, y2. By simple geometry, we can show that the coordinates x2 and y2 will be related to x1, y1 and the angle theta. By this equation, x2 is equal to x1 cos theta minus y1 sin theta. y2 is equal to x1 sin theta plus y1 cos theta. Hence the complete matrix representing proper rotation by an angle theta in the anti-clockwise direction. The anti-clockwise direction is taken as positive direction. It will be cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1, x1, y1, z1. That will give x2, y2 and z2. Z2 will be evidently the same as Z1. Now, improper rotation. Denoted as Sn, which is equal to Cn into sigma h. The changes in the x and y coordinates on improper rotation will be the same as changes occurring to x and y coordinates on the proper rotation Cn. The difference is that because of sigma h, the z coordinate will change to its negative value. So the matrix representing improper rotation will be like this: cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, minus 1 corresponding to Sn. This will multiply into x1, y1, z1, giving x2, y2, z2. z2 is the same as minus z1. Having understood how to create matrices for the transformation of a general point denoted by the coordinates x, y, z. Now we shall write the matrices for the operations for C2V group to which water molecule belongs. We know that the operations for C2V group are identity C2Z, sigma V X Z and sigma V dash Y Z. On the basis of the general coordinates of a point, the matrices are easily written under identity. It is a unit matrix of order 3. C2 Z coordinate will not change, others change to their negative values. This is X Z, so X and Z will not change. Here it is Y Z, Y and Z will not change. These are the matrices. This set of matrices so generated for a particular group C2V, it is called representation of the group. We call it as representation. The coordinates x, y, z are called the basis functions using which we have created this 3 by 3 matrix set. Each matrix is called a representative and a collection of matrices is called a representation, being matrices of order 3. The order is the same as the dimension of the representation. This particular representation is a 3-dimensional representation. These representations are expected to interrelate one another in a way exactly parallel to the way in which the symmetry operations are interrelated. For example, from the group multiplication table of C2V, we know that sigma V X Z multiplied by sigma V dash Y Z will give the operation C2Z. Let us see how the matrices representing these operations behave. Sigma V X Z is 1 0 0 0 minus 1 0 0 0 1 and sigma V dash Y Z is minus 1 0 0 0 1 0 0 0 1. Because they are similarly block factored, their multiplication is quite easy. These are the non-zero elements. Here you will write product of 1 and minus 1, that is minus 1. Here you will write minus 1 into 1, minus 1. Here you will write 1 into 1, 1. So we are getting a matrix expected for C2Z operation. The matrices enact or behave exactly like the symmetry operations. Every operation is its own inverse in the water molecule. Think of C2Z. The matrix representing this is minus 1 0 0 0 minus 1 0 0 0 1. And what is the inverse of this matrix? Being an orthogonal matrix, its inverse is, if this is A inverse is simply the transpose of it. So what is the inverse of this? You write the transpose. First row is written as the first column, second row is written as the second column, and the third row is written as the third column. And you are getting the same matrix. So every operation is its own inverse. So we shall write a concise sentence to define the representation of a group. Make a special note of this sentence. Let me rub this off. A set of matrices each corresponding to a single operation that can be combined among themselves in a manner exactly parallel to the way in which symmetry operations combine. This is a beautiful, concise sentence defining representation of a group as given in the text by F.A. Cotton. From this essence of this defining sentence is that these matrices are generated to echo the properties of operations. They echo, they just exactly play the same role as operations. That is why they are called representations. They echo the properties of symmetry operations. We have noticed that the 3 by 3 matrices generated earlier for C2V group are similarly block factored. I have to write this again. 1 0 0 0 1 0 0 0 1 minus 1 0 0 0 minus 1 0 0 0 1 1 0 0 0 minus 1 0 0 0 1. Here it is minus 1 0 0 0 1 0 0 0 1. They are similarly block factored. The non-zero elements are present along diagonal blocks like this. This has an important consequence. It is possible to pick out the numbers from corresponding blocks from first row, first column, 1, minus 1, 1, minus 1, and link it to the first basis function x. Similarly, y corresponds to 1, minus 1, minus 1, 1, and z corresponds to 1, 1, 1, 1. You can call these as one-dimensional matrices. If you want to call it as a matrix, we are supposed to write square brackets, but because it is one-dimensional, writing the matrix with the square brackets and without square brackets make no difference. If they are written with square brackets, you can call them matrices. Without square brackets, they are the characters of these matrices. For a one-dimensional matrix, the matrix element and character are the same. So visually we have broken or split the three-dimensional representation into 3 one-dimensional representations. One dimension being the lowest cannot be reduced further. Therefore, these one-dimensional representations obtained are called irreducible representations. I will denote it by the notation IRREPUB, irrep. And the original three-dimensional representation, which has been split into 3 one-dimensional components. The original one is called a reducible representation. For a particular point group, the number of reducible representations can be very, very large. A question can naturally come. How many representations can one write for a point group? The answer is a very large number, limited by your cleverness in choosing the set of basis functions. The basis functions usually chosen are the coordinates of a general point, as we have already done. You can put unit vectors centered about every atom parallel to the x, y and z directions, and write a representation on the basis of this collection of unit vectors. Every atom has got 3 vectors. For a molecule like H2O with 3 atoms, there can be 9 vector components, so it will be a 9 by 9 unit, 9 by 9 matrix. Other basis functions can be orbitals or collection of orbitals in the molecule, any vector or vector components pertaining to the molecule, any molecular property like its dipole moment or the molecular mass itself. It all depends on your cleverness in choosing basis functions to decide on how many representations of higher dimensions one can write for a particular point group. But the number and the type of irreducible representations are limited and of prime or fundamental significance. Every point group has a limited number of irreducible representations, and usually it can be one-dimensional. It is also possible that the irreducible representation of a molecule is truly irreducible even if the dimension is 2 or 3. There are 2-dimensional irreps or even 3-dimensional irreps. The knowledge of the characteristic irreducible representations for a particular point group is obtained from a fundamental quality for the point group, a fundamental feature for the point group known as character table. Character table spells out the number of type of irreducible representations which are of very, very fundamental significance for a particular point group. So naturally, we are stopping here with the hope that in the next video we have to discuss character table and the various theorems pertaining to character table. Until then, bye.